Let's continue our journey to transport layer of the TCP IP model. Today we will take a deeper look into the Transmission Control Protocol, or TCP. Honestly speaking, I can guarantee that you will not have to deal with the TCP protocol directly at the junior network engineer position. However, when you get to the higher position, understanding TCP protocol gives you the confidence to troubleshoot complex network issues. We will talk about the following topics in this video. First of all, we will give a brief description about the TCP. Next, we will explore in detail on TCP operation, how it establishes the connection with its peer to transfer data, then terminate the connection. Finally, we will sum up our video with the keynotes. TCP is a full-duplex, connection-oriented, reliable, and accurate protocol at transport layer. TCP protocol operations may be divided into three phases. Connection establishment phase, where connections must be properly established in a multi-step handshake process before entering the data transfer phase. After data transmission is completed, the connection termination closes established virtual circuits and releases all allocated resources. To understand TCP protocol operation, let's analyze the telnet activity happening in this diagram. As you know, telnet is an application layer protocol that allows a user on one computer to log in and perform tasks on a remote computer. Telnet uses TCP to transport data. TCP assigns port 23 for telnet data. In this diagram, a user from client's computer telnets to the server and view the server configuration. Let's see how TCP transfers telnet data from client to server. To provide the service, telnet server does a passive open to port 23 and starts listening on port 23. It does not initiate any protocol on the wire. The client generates a random port 22143 and does an active open to port 23 on the server, which triggers the TCP protocol send message. Let's look into the send message in detail. This is the send message, which relative sequence number 0. It's sent from telnet client to the server. In my opinion, the most important information in the send message is the maximum segment size. As we know, the data coming from application layer will be segmented, then put into the data field of a protocol in transport layer. The question is how much the data is segmented. In TCP, the answer found in maximum segment size, MSS. MSS specifies the largest amount of data in bytes that a host can receive in a single TCP segment. By default, IPv4 hosts are required to be able to handle an MSS of 576 bytes. However, there are 20 bytes of TCP header and 20 bytes of IP header. Therefore, MSS equals 536 bytes. In fact, a host selects its MSS based on capacity of the physical connection. In our case, it is Ethernet connection which can handle 1500 bytes. Therefore, the host advertised its MSS equals 1500 subtract 20 equals 1460 bytes. The hosts then advertise their MSS in the option field of the TCP header to each other, and the lower number of MSS between the two hosts will be used. If the server is available, it will respond with a send ACK message. Let's look into the send ACK message in detail. This is send ACK message. It is sent from the telnet server to the client. It acknowledged that it had received the send message from the client and expects the next data message with sequence number 1. It also tried to send with the client with the relative sequence number 0. It also advertised its MSS information. Let's talk about the sequence number and acknowledgement number. All bytes in a TCP connection are numbered, beginning at a randomly chosen initial sequence number, ISN. In Wireshark, ISN is considered 0. Therefore, it is called relative sequence number. An actual sequence number is highlighted in the screenshot below. The sequence number is the byte number of the first byte of data in the TCP segment. The sequence number is always valid. The acknowledgement number is the sequence number of the next byte the receiver expects to receive. If the ACK number equals 10, which means receiver acknowledges receipt of 9 bytes and expects to receive the data with the sequence number equal 10. The acknowledgement number is only valid when the ACK flag is set. The only time the ACK flag is not set is during the first packet of connection setup. After receiving the send ACK message from the server, client responded with the ACK message. Let's look into the ACK message in detail. This is the ACK message. It is sent from the Telnet client to the server. It acknowledged that it had received the send ACK message from the server and expected the next data message with sequence number 1. The virtual circuit is now established, which allows the data to transfer. As you know, the Telnet client and server are now exchanging the data. To make it simple, we only reconstruct the data segments sent from the client to the server to build the data that the server received from the client. Here is the first Telnet data message since it has a relative sequence number 1. It has push flag to allow the sending application to start sending the data even when the buffer contains data less than MTU. It's sent from client to server. It sent 9 bytes. Therefore, the next sequence number is 10. In this message, you see the Telnet data. Here is how the data received at the server. This is the next message. Since it has the sequence number 10, it sent 3 bytes, so the next sequence number is 13. Here is how the data received at this server. This is the next message. Since it has the sequence number 13, it sent 3 bytes, so the next sequence number is 16. You may also notice that the byte in flight is 6, which means it has not received the ACK message after sending 6 bytes. Here is how the data received at the server. Here is how the data received at the server after receiving this Telnet data message. Here is how the data received at the server after receiving this Telnet data message. ACK message 26 means it confirmed that it received 25 bytes and it expected to receive the next data message with the sequence number 26. Here is how the data received at the server after receiving this message. Please notice that the byte in flight now reduced to 1 and the byte sent is also 1 after it received the ACK message. The data transfer phase continues until either the server or client closes the virtual circuit. Let's take a look at our case. It is the server that closed the circuit by sending the finished message. Here's the finished message from the server. It sent the server to the client. This is the flag of the finished message. When the client received the finished message from the server, it responded with the ACK message. Here's the ACK message. From now on, the server can no longer send data. The client now sends the finished message to the server. Here's the finished message from the client with the finished flag set. The server then responded with the ACK message and the virtual circuit is now closed. You may notice the window size value kept changing during the data transfer. The window size controls how much information is transferred from one end to the other before an acknowledgement is required. In TCP IP, it measures by counting the number of bytes. For example, when the Telnet client receives a window size 10, it can send up to 10 bytes of data to the server without receiving the ACK message from the server. As you may remember, it showed in the Wireshark as the byte in flight. Window size is used when congestion occurs. The receiver will advertise a smaller window size, which forces the sender to stop sending data until it receives the acknowledgement, which will slow down the sender until congestion is resolved. TCP protocol operations are divided into 3 phases: connection establishment, data transfer, and connection termination. To establish a connection, TCP uses SYN, SYNACK, and ACK messages. To transfer data, TCP uses sequence number to identify the first byte of data in a TCP segment, ACK number to confirm the receipt of data and the sequence number of the next byte it expects to receive, MSS to inform how much data for its segment, window size to control how much data it can receive after sending ACK message. Connections are full duplex, that is, 2 distinct channels from server to client and client to server. Either side independently closes its channel. A close is signaled by the finish flag. The fin packet is acknowledged with a sequence number 1 higher. To close both channels takes 4 messages: a fin, its ACK, then the other side's fin and its ACK. This is the end of this video. Thank you very much for watching.